So the problem is to find the average velocity of, say, a rock thrown on Mars in accordance with this problem. Well, let me help you understand why we're looking at the average velocity and what that really means. We'll look back at this table. I'm just going to take a couple coordinates from this table. So we've got your x coordinates and your y coordinates. So let me just pick, say, this one, 1 and 8.14. And then we'll pick another one, say 2 and 12.56. So this is t, which is your time, and this is h, which is your height. Well, what we're going to do is we're going to find the slope of a line between these 2 points. And I hope that you remember that slope is given this way: y2 minus y1 over x2 minus x1, right? That's slope. So in this particular case, it's going to be 12.56 minus 8.14 divided by 2 minus 1. Just the difference in the y's divided by the difference in the x's. If you step back from this a little bit and take a more critical look at this, you'll understand this a little bit better, why we're calling this the average velocity. So let's remind ourselves about something here, an old formula from algebra. Distance equals rate. Does anyone know what else? Rate times
time.
Time, yeah. Distance equals rate times time. But what if you took and divided both sides of this relationship by t? You get distance divided by time equals rate. Oh, okay. Now, if you look here back at our formula, this is your height. That's in meters. What units do we have here? That was in units of seconds.
Time.
Yeah. So this answer here is going to be in meters per second. So, oh, okay. And if you actually did out the math here, you get 4.42 divided by 1 meters per second. That's a velocity. That's an average velocity. Now, it's not an instantaneous velocity, and we're going to have to understand what an instantaneous velocity is going to mean. But that's why I gave you this link here to this Desmos demo, so we can try and understand what all that means. I think I might have started this out at I equals 8. Should have started it out at I equals 1. This actually goes a little bit past what the problem is asking because I give you an extra point, but that's really just for visual context. What we're seeing here is a line that connects a couple points on our graph. If you calculate the slope of that line, it's the average slope. It's what's happening to the function on average. It's not what's happening at any particular instant. You notice the function does a lot of things. For instance, right here, near t equal 1, the function's increasing pretty quickly. But as we get closer over to here at t equal 2, the function's not increasing as quickly. And then right here, the function levels off right around here. And then it starts decreasing. So a lot of things happen with the velocity of this function. It's not, or the way this function changes, it's not just doing the same thing throughout this whole interval. Now, what our goal is to try and find out what's happening closer and closer to this point right here at 1 and 8.14. And that's what we're going to use our little slider here for. Let's go from 1 to 2. And in fairness, this is where the actual problem starts. The problem starts here. It says, okay, find the average slope of a line between these two. And you see our calculation here matches what we just did on paper. This is changing at an average rate of 4.42 meters per second. But now we're going to bring that closer. We're going to bring that to this point. So dial it up to I equals 3. And now our rate of change is steeper, right? It's 5.35 meters per second. And we're going to continue to get closer and closer and closer. So the points that we're going to look at are going to help us find the average velocity over these particular intervals. So we've done the first two. The average velocity over this interval was 4.42. We calculated that by hand. This one we relied on Desmos for. We got 5.35. So the next one accordingly should probably give us 6.094. Let's see that that's true. And you can kind of see what's happening. As this point gets closer, the slope of that line is going to get steeper and steeper. So if we move that up to I equal 4, it's steeper. Then I equals 5. Now the change that we're going to see is going to just disappear because it's getting so small. We're looking at a really tiny interval between 1 and 1.01 or 1 and 1.001. So the interval is getting really, really short. It's still an average velocity, but that average is over a really, really tiny time interval. And what's happening is that you're getting closer and closer to what must be the instantaneous velocity. What's happening with that function right at that second, not over some interval, but right there, then and now. So let's pursue this a couple more steps here. And you're not really seeing any change in the line, but you are seeing something going on with the slopes here. And there's the last one. So let's take a look at the handout. And here's the slopes for our various intervals. I didn't write intervals 6 and 7 here, but you can kind of see what's going on. Do these numbers seem to be getting bigger and bigger and bigger and bigger forever, or are they getting close to some number?
Close to some number, for sure.
Yeah, thanks, Matt. So it looks like they're getting close to some number. And does anyone want to venture a guess what that number is? What are those getting close to? What's it look like?
6.28.
Yeah, 6.28. So 6.28 is our best guess for what's called the instantaneous velocity. That is, if you can measure the speed right at that second, that's what it would be. My dad tells me stories about how they used to catch people speeding on the highways. And what they would do is they would lay out 2 air hoses, maybe 100 feet apart from each other. And when you went over the first air hose, a little timer would start. And then when you went over the second air hose, another timer would start, or the timer would stop. You know the distance between those two, distance equals rate times time. It's easy to solve for your average rate of speed. But there's a problem in that. It's your average rate of speed. If you were a savvy driver and you saw that first hose on the road, what would you do? You don't want to be caught speeding. Yeah, you slow down, right? And you got time to slow down because you've got a certain amount of distance between the first hose and the second hose. So yeah, it gives you time to slow down. And that was a kind of a problem. They were getting an average velocity. But that all changed when they invented radar guns. And radar guns gave you an instantaneous velocity. They're like, oh, okay, I don't care how fast you're going after you tap the brakes. How fast are you going now? And that's what we're doing with calculus. Calculus is going to start out by looking at what's happening to a function now, how that function is changing at an instant, not over some time interval, but over an instant. And in this particular case, that instantaneous rate of change, kind of the answer to part B here, would be 6.28. And we initially get at that simply by trying to look at a limit. So 6.28 meters per second. Nice. So that's where we're headed in this course, at least initially, is trying to find an instantaneous velocity or an instantaneous rate of change. And it's going to involve several things. It's going to involve limits. It's going to involve some algebra. It's going to bring this all together. And at the end of the course, we're going to be doing kind of the opposite of that in a certain way. So are we okay with this first example? Doing all right with that one? Is there anything that maybe I went over a little too quickly you'd like me to discuss again?
Is there somewhere that we can find this?
So I'll be posting this video on YouTube.
Like the problem, or is that just on the screen?
It should have been a handout that I put in the chat.
Oh, okay, thank you.
Yep. Anything else? All right.